All right, this is my third time starting this, so we're going to just go with whatever happens in this video. Welcome to your fourth lesson for this unit. We're going to be finishing up talking about collisions, elastic and inelastic. There's one more case that I want us to kind of discuss on Friday with like angles, but we'll get there, and I want to be there in person for that one. So far you know a lot about collisions. We've analyzed a bunch of collisions. We've talked about impulse, momentum, all that good stuff. But there is one case that we right now can't solve for. We're going to talk about that case today. Not that a long lesson would be bad. It would be a wonderful thing you'd be learning, but I'm trying to keep this video to like 15 minutes. So we're going to start by just evaluating the two types of collisions or defining them again. So the ones where we have things that stick together, like a train car traveling at some kind of velocity VA1, another train car traveling VB1, but then they kind of couple together. So now they're traveling at this common velocity V2. That'd be called an inelastic collision, where they stick together and then travel at the same velocity. Think about those football examples from yesterday, right? If you tackle someone, then you're kind of traveling with them. Our other type of collision, what's it called? It's where two things will come together, bounce, and then bounce away from each other. That's going to be called your elastic collision. So think about pool. When you play pool, there's a lot of elastic collisions happening. Sometimes the what is it called? The cue ball will hit and then it will stay still and kind of transfer all of the momentum to the other ball. Sometimes it will get knocked backwards. Sometimes it will still move forward, but they're not really sticking together. That's an example of elastic collisions. So far we have the conservation of momentum equation itself. When we have objects that bounce apart after a collision, when we're dealing with elastic collisions, the conservation of momentum equation is helpful. So that's that MA VA1 plus MB VB1 equals MA VA2 plus MB VB. There we go. 2. Great equation, but what if they're asking for both velocities after the collision? What if we know how to measure the two velocities of the two different objects before the collision, but then they're asking us, okay, well, then what happens afterwards? I have two unknowns right now. Two unknowns, maybe you can guess, I need another equation. Or you could just read the sentence on the slide that says we need another equation to solve for both unknowns. So here's the part that I don't love, but it's how we're going to do things, all right? We have yet to talk about energy. So at some point, we're going to talk about kinetic energy. Once we know about energy, we could derive this new equation, this helpful equation. I am just going to give you this equation right now. And then when we get into energy in a couple of weeks, I want us to kind of connect back a little bit and see, oh, okay, that's how we were able to use this. So here's your equation for elastic collisions. VA1 minus VB1 equals VB2 minus VA2. And right now, I am just telling you this equation is our special elastic collision equation. We derive it based on energy equations. For right now, in this chapter, we're going to say, hey, I know this equation works, it exists, and we're going to solve some of our problems here, and we're going to kind of tie everything back together. At some points in physics, things aren't separated into perfect boxes and perfect units. They all kind of come together. So we just have to learn them in a certain order, and we'll get back into it. Okay, so this is your other equation. Write this one down. Make sure that you're keeping the order of things straight here. I did write it correctly. It's VA1 minus VB1, VB2 minus VA2. With these two equations, I can solve for two unknowns. So I have 3 examples for us to walk through. Here's the first one. We have a billiards ball. So I know the mass is 1 kilogram. I know VA1 is going to be that 3 meters per second towards another ball, and B equals 2 kilograms. It's at rest, so I could say VB1 is 0. After the collision, the balls bounce apart. Find each of the final velocities. So what is VA2? What is VB2? I mean, I guess they could be the same, but if they're bouncing apart, they probably won't be. So that's why we have two unknowns, two separate things here. The two equations we're going to use, our conservation equation, MAVA1 plus MBVB1 equals MAVA2 plus MBVB2. And, maybe I shouldn't write plus, that could get confusing. And VA1 minus VB1 equals VB2 minus VA2. Those are our two equations we can use here. Let's start with the conservation of momentum one. I'm going to just plug everything in. So I have 1 kilogram times 3 meters per second plus, well, this whole term is going to drop out. Okay, so plus 0 because my initial velocity for the second ball is just 0. It's at rest. So then that's going to equal 1 kilogram times VA2 plus 2 kilograms times VB2. Okay, I can clean it up a little bit. Let's go ahead and drop our units just for clarity. Over here I'm going to have 3. Over here I'm going to have 1 VA2 plus 2 VB2. Okay, so this is one of my equations. Let's work with our other equation, and then we can combine them up, use a lovely system of equations. So for our second equation, VA1 is 3, VB1 is 0, VB2 I don't know, VA2 I don't know. Clean it up a little bit. I'm going to get 3 equals VB2 minus VA2. So those are our two equations. You can take your pick. You can use elimination or substitution when solving for a system of equations. In this case, I see that I have VA2 and a negative VA2. So what I'm going to do is probably just elimination here, and I'm going to rewrite my equations over here. 3 equals VA2 plus 2 VB2, and then I'm going to rearrange the second one a little bit. So minus VA2 plus VB2. I'm going to go ahead and add these equations together. I'm going to get 6. These two would cancel out, equals 3 VB2. VB2 is going to equal 2 meters per second. So that's VB2. That's for the second billiard ball, the one that we hit, the one that was originally at rest. Now I need to go ahead and solve for VA2. You can use either equation at this point. I think this one looks a little easier for me. So 3 equals 2 minus VA2. Rearrange that a little bit. I'm going to end up getting VA2 equals -1 meters per second. And once again, make sure the signs make sense, right? If I'm assuming that I started with a pool ball going this way and another one just at rest, well, yeah, I think it could be logical for this one to then start moving in this direction and this one to, after the collision, start moving away, but at a little bit of a slower speed. I think, yeah, that logically could make sense. So that's what's going on here. If you want, you can experiment with the mini pool table and see if you can try to see some of these different shots in action. See, are there different ways that you could hit it to get the cue ball to stop, to get the cue ball to bounce backwards. Test it out, see what's up. All right, second example. So this one's kind of cool because now we're dealing with chemistry a little bit. We're dealing with protons, electrons a little bit. That's really fun. And we're using this entirely different unit of mass. So a proton of mass 1.01 U, or unified atomic mass units, is traveling at this really, really fast speed. It collides head-on with a helium nucleus, and they're giving us the mass of that, which is initially at rest. So I have a couple of givens here. MA equals 1.01 U. And here's the thing, don't convert. This goes against a lot of the things that I've told you. Welcome to science, where you learn something and then you learn something else, and then it all ties together and it's part of the process. Because mass is in each of my terms in my conservation of momentum equation, I'll just jot it down over here again. MAVA1 plus MBVB1 equals, where did this line come from? equals MAVA2 plus MBVB2. Okay, so since there's a mass in every single term, the units of mass are just going to cancel out. So I can use any units of mass I want. And I think we've seen this in some other equations too. I know you guys kind of saw this with some of those torque equations. Did I really have to convert from centimeters to meters? In some cases, maybe not, because it would cancel out. So I'm not going to waste time trying to convert this atomic mass unit into kilograms. Leave it alone. It'll cancel out. So M of A, let's call A that proton, and then M of, let's use the helium symbol, is going to be 4.00 U. I know those two things. I know VA1 equals 3.6 times 10 to the 4th meters per second. I know VHE1 equals 0. We're going to solve using the same process as the last example. I have my two equations, so go ahead and plug in there. This term is going to cancel out because I'm initially at rest. So I have 1.01 U times 3.60 times 10 to the 4th meters per second equals 1.01 U VA2 plus 4.00 U VB2. And here you're going to see that U is going to cancel out from every single term, so it doesn't really affect us tons. I'm going to simplify a little bit. Over here, when I multiply, I'm going to get 36360 equals 1.01 VA2 plus 4.00 VB2. That's your first equation. Hang on to that one. We'll get back to her in a second. Then we're going to use our special elastic equation, VA1 minus VHE1 equals VHE2 minus VA2. I know my speed over here will just cancel out, so I'm left with 36000. You can keep the scientific notation if that helps you. I think sometimes when we're actually working with the equations, it's nicer to have the larger number. Up to you, man. That's up to you. It's going to equal VHE2 minus VA2. That's my second equation. Maybe for this one, substitution would be better. In my humble opinion, I would definitely say substitution would be better. So I'm going to rearrange and I'm going to solve for VHE2. So VHE2 is going to equal 36,000 plus VA2. And I'm going to take this and I'm going to plug it in to VHE2 up there. So I'm going to end up with 36360 equals 1.01 VA2 plus 4 times 36,000 plus VA2. Go ahead and distribute that 4. You're going to get some big numbers here. That's okay. 36360 equals 1.01 VA2 plus 144,000 plus 4. Let's drop those zeros. Why not? VA2. You can combine up your two VA2 terms at this point. You can subtract 144,000 from both sides. When you do that, I'm going to write our final answer. You're going to get VA2 equals negative 21,500 meters per second. So that's what we're looking for VA2. Once again, pause, make sure the math works out for you, okay? So I did the setup here. I just skipped a couple of steps at the end there. I trust your algebra skills. I know you can do algebra. We should get a negative 21,500 meters per second for VA2. At this point, I need to find VHE2, so let's use this equation over here. VHE2 equals 36,000 plus what we just found, negative 21,500. VHE2 is going to give us 14,500 meters per second. And that is the answer to this problem. So you see what we're doing here? It's similar to what we've been doing. You have your conservation of momentum equation. Now we're adding in this little special secret energy equation that we don't yet know the derivation for. Eventually we will, but I'm going to just ask you to trust me on this one, and then we can prove it later on. and then you're just doing a system of equations. One final example, folks. We have a softball. Mass of the softball is 0.220 kilograms. It's moving with a speed, VA1, of 8.5 meters per second. It collides head-on and elastically, so I know I'm going to bounce apart with another ball. Could we assume the mass of the other ball? I don't know. Actually, they're telling us to calculate it, so don't assume the mass of the other ball, but we can say that its initial velocity is 0. It is at rest. After the collision, the incoming softball bounces back with a speed of 3.7, so I know VA2, in this case, if it's bouncing backwards, just be super careful with your sign, negative 3.7 meters per second. They're asking us to calculate VB2, and they're asking us to calculate MB. So you have your two equations. Which one do you want to start with? Well, I know 1, 2, 3 out of 4 velocities. So let's start with our super secret special velocity equation. VA1 minus VB1 equals VB2 minus VA2. And let's go ahead and plug everything in. So I have 8.5 meters per second minus 0 equals the thing I'm trying to find, VB2, minus negative 3.7 meters per second. Okay, so that 0 just gets canceled out. I'm going to subtract 3.7 from both sides, and we're going to end up with VB2 equals 4.8 meters per second. So that's the answer to part A. That's going to be the velocity of the oncoming, the velocity of the target ball. So remember, something was being thrown at another object at rest. And then after that, this object is going to keep on going. This object is going to bounce back. Now that we know that velocity, we can use our conservation of momentum equation to calculate that second mass. So MAVA1 plus MBVB1 equals MAVA2 plus MBVB2. Okay, I know this whole term cancels out because that one just started at rest. Over here, we're going to get 0.22 kilograms times 8.5 meters per second equals 0.22 kilograms times VA2 is negative 3.7 meters per second, plus, didn't have enough room there, MB, that thing I'm trying to find, 4.8 meters per second. All right, let's clean it up a little bit. 0.22 times 8.5, plug that into your calculators. I got something around 1.87. Your units, remember, momentum is going to be kilogram meters per second. We can just kind of drop those until the very end. 1.87, and then over here, 0.22 times negative 3.7 is going to give me negative 0.814 plus 4.8 times that mass that I'm trying to find. So I'm going to add 0.814. We have 2.684 equals 4.8 mass of the target ball. Divide by 4.8. The mass of the target ball should be 0.56 kilograms. And please, as always, plug this stuff in on your own. Make sure these numbers are lining up, are making sense. Trust your own work, right? Make sure that it's going into your calculator and spitting out a solution that makes sense to you too. All right, that is our final example. Go ahead and get started on your homework if you want to. It's just a bunch of problems where they give you mass and velocity and they're asking for final velocities just to give you just some extra practice getting comfy with both of these equations. And then we'll have our lab tomorrow. All right, was it under 15 minutes?